everyone, my name is Yuejia Wu from Inner Mongolia University, China. My presentation paper title is A Neighborhood-Aware Graph Self-Attention Mechanism-Based Pre-training Model for Knowledge Graph Reasoning. This paper has been accepted in Information Sciences. A knowledge graph is essentially a semantic network that reveals the relations between entities and can formally describe things and their relations in the real world. It represents and stores the knowledge through fact triples in the form of HRT, where H, T, and R represent the hand entity, the tail entity, and the relation between them of the fact. Existing KGs such as Freebase, DPPDR, and WordNet have been widely used for knowledge-based question answering, semantic analysis, personalized recommendation systems, and so on. However, the KG is usually incomplete and sparse, limiting its performance in the above applications. Next, we give the M-Critters definition of incompleteness and sparsity of KG. The first is incompleteness usually denotes missing the whole fact triple or missing one part of the fact such as hand entity, tail entity, and the relation between them. The next is sparsity, includes entity sparsity and relation sparsity, which refers to the small proportion of the number of entities and relations in the total number of facts. Knowledge graph reasoning is one of the main methods to solve these problems. It inferences new knowledge based on the existing knowledge in the KG, and its main objectives include in-prediction, fact prediction, entity prediction, and relation prediction. In this paper, we will focus on achieving the goal of link prediction, which uses a scoring function to judge the possibility of the given relation that belongs to the KG. Recent studies have shown that there are two mainstream approaches to realizing the link prediction tasks in KGR. One is embedding-based representation methods, and another is neural networks-based methods, including the CNN-based methods and GNN-based methods. In addition, due to the stronger modeling and learning ability of transformer architecture, more and more research work has introduced it into KGR fields for modeling and representation of KG, which has gradually become a research branch of the GN-based KGR methods. Although these methods can obtain useful knowledge, there are still four limitations that influence the performance of link prediction tasks. The first is that the graph feature extraction is insufficient. In the GNN-based KGR approaches, the embedding representation of the entity in KG should be extracted at first. Whether more effective information can be extracted from data will directly affect the effectiveness of encoding and the link prediction tasks. However, the existing model directly sends a simple representation of the entity to the encoder for learning and training, resulting in the lack of ability to learn the hidden features of the data. Second is that noises are introduced in graph feature extraction. Because the graph attention network has the absolute advantage in processing directed graphs and can dynamically assign weights to the neighborhood entities, we use it to evaluate the first problem and obtain graph features containing entity neighborhood structure information dynamically. However, it may introduce noises, that is, irrelevant entities information, because it treats all neighborhood entities equally, which may lead to misleading inference results. Third is that the path connection coefficient between entities is not considered. The entity pair correlation index is the key to measuring whether relations can be generated between entities. The existing methods usually use the number of common neighbors, degree, and clustering coefficient of entities to measure the similarity of given entity pairs. However, in the actual calculation process, we discovered that the path connectivity coefficient is also one of the factors affecting the similarity calculation. That is, it can make the model sensitive to finer-grained differences between entities for discussing the contributions of each neighborhood entity. Last part is the neighborhood information acquired are always insufficient. Existing GNN-based KJR methods learned and trained graph structure features by using GNN architectures such as GCN, GET, and transformer to accomplish the link prediction tasks. When acquiring the neighborhood entity information, they usually regarded the KJ as a hierarchical structure and carried out hierarchical neighborhood aggregation operations on it. This method of pre-division before encoding may lead to the loss of information during the division phase and affect the prediction accuracy. Therefore, it is very important to pay more fine-grained attention to neighborhood information in the global knowledge graph when calculating attention scores. To improve those issues, we present a KJR pre-training model based on a neighborhood-aware graph self-attention mechanism, referred to as NAKJR. NAKJR consists of two phases. The entity pair similarity differences enhance the graph attention network and the neighborhood-aware self-attention mechanism. The ENGET can encode useful entities using the weighted characteristics of single-hop neighborhoods to convert KG into entity representation vectors, which reduces noise introduction. Then, the NASA can model entity similar attention to capturing plentiful, valid neighborhood information from the perspective of global knowledge graph. Furthermore, we design a pre-training pattern based on the neighborhood-aware random walk sampling and the general subgraph-based structure-aware sampling. We can improve the model's generalization ability. The main contributions of this paper are as follows. First, we propose a two-phase neighborhood-aware graph self-attention mechanism-based KJR model representing KJ with abundant neighborhood information. To the best of our current knowledge, this is the first approach that designs a neighborhood transfer probability and ends it into with attention calculation for specifying the contribution of different neighborhood entities to the current entity characteristics when obtaining knowledge graph features and then ends an anti-similarity matrix into multi-hand self-attention calculation to obtain more stable and effective neighborhood information from the whole graph without interfering with the knowledge graph structure. Second is, we present a path connection coefficient-based entity pair similarity calculation algorithm, namely PCCA, to support the neighborhood selection criteria. Compared to the previous calculation algorithm, PCC is the first method that considers the path connectivity coefficient between entities, which is more sensitive to entity similarity and can obtain a more fine-grained similarity score to differentiate the contribution of neighborhood entities. Then we design a two-stage pre-training and fine-tuning pattern comparing PCC-based neighborhood-aware random walk sampling methods and general subgraph-based structure-aware sampling methods to enhance the scalability and generalization of the model while obtaining better training results under both low and high-dimensional knowledge graph. Finally, we conduct extensive comparison and evaluation experiments on 4 benchmark datasets, and the results illustrate that a proposed KGR model, NA-KGR, can effectively improve the performance of existing GNN-based models and obtain optimal experimental results. As shown in Figure 1, we give a detailed overview of the NA-KGR model from the perspective of implementation methods. It can be found that the proposed model is equipped with two graph neural network phases and a pre-training and fine-tuning task. The first phase is the enhanced graph attention network, which converts a knowledge graph into anti-representation vectors and incorporates the effective neighborhood information to the second phase. The second phase is the neighborhood-aware self-attention mechanism, which designs an adaptive similarity score matrix and adds it into the multi-hand self-attention score calculation to effectively measure the influence of entities' neighborhood so that obtain fine granularity of entity-neighborhood information and enhance reasoning effect. The third part is the pre-training and fine-tuning task, which presents a neighborhood-aware random walk sampling methods, compares a general subgraph-based structure-aware sampling methods to train our model, which can enhance its extendability and generalization. That is, can adapt to the changes in parameters or other variables and have the adaptabilities to new samples that can learn the rules hidden behind the data. That's all. Thank you for listening.